Welcome to this session on drilling optimization, well-designed process to execution. This is submodule 4 of 4 in our series. In this session, we'll be exploring the transition from well design into real-time execution, focusing on risk models, time and cost models, and the critical role of forecasting. Let's begin by looking at our learning objectives. In this submodule, our focus is on 5 key objectives. First, we will explore how risk models are applied throughout the design and execution phases, giving us a structured way to identify, evaluate, and mitigate hazards. Second, we'll examine time and cost models, showing how they can be applied to drilling operations to balance technical performance with financial constraints. Third, we'll learn to differentiate between design forecasts and the realities of execution data, highlighting the importance of calibration. Fourth, we'll cover the use of daily forecasts to raise hazard awareness and improve proactive mitigation across the rig team. Finally, we'll see how calibration of models enhances both performance and decision-making. These objectives together give us a framework for optimizing drilling operations from planning to real-time execution. With that foundation, let's now begin with risk models. Risk models form the backbone of safe and efficient drilling operations. At their core, they allow us to identify, quantify, and prioritize drilling hazards. Quantified drilling hazards mean that we don't just list risks, we assign measurable values to their probability and severity. This approach gives us a clear picture of which risks demand the most attention. We also use structured identification techniques to uncover risks that may not be obvious, such as hole instability, lost circulation, or equipment failures. Once identified, we define mitigation measures that provide practical ways to reduce both likelihood and impact. For risks that cannot be fully eliminated, contingency plans are established to ensure we have a prepared response. Taken together, probability, severity, identification, mitigation, and contingency planning give us a comprehensive framework. This isn't just paperwork. It's an operational mindset that helps the team manage uncertainty while maintaining performance. On this slide, the bulleted list highlights these key elements in sequence. As we move forward, we'll see how risk models differ in application between the design phase and execution phase, giving us both a proactive and reactive perspective on drilling hazards. In the design phase, risk models play a predictive role. This is where we define potential events and assess their severity before drilling begins. For example, if wellbore instability is a potential event, we estimate how severe the impact could be, ranging from lost time to complete sidetracking. Next, we assign probabilities, asking how likely is this event to occur. This probabilistic view, combined with severity, lets us prioritize. The model also evaluates the likelihood of overall success for the well design, which is vital for economic justification and stakeholder approval. We also embed procedures directly into the model, ensuring that mitigations are not theoretical but operational. Equipment requirements are tied in as well. If we expect potential kicks, for example, then BOP specifications and testing requirements are defined in advance. Contingency planning is another key element. Whether it's backup mud systems or a sidetrack strategy, the model ensures we have predefined options. Forecasting rounds out the picture, giving us visibility into what is most likely to happen. This structured, forward-looking application of risk models during design lays the foundation for safe and efficient execution. Next, let's see how the model adapts once drilling is underway. Once drilling moves into execution, risk models shift from prediction to real-time application. Instead of defining possible events, we are now analyzing actual events as they unfold. For example, if lost circulation occurs, the model guides us in quantifying its impact on both time and cost. Time and cost analysis becomes central in execution. Every decision, whether to continue drilling, to pull out of hole, or to sidetrack, has financial implications. The risk model gives us a structured way to weigh those trade-offs quickly and consistently. Decision-making in this phase also relies heavily on management of change. As operations deviate from plan, the model helps formalize those changes, ensuring we assess their impact before implementation. Procedures continue to play an important role, giving the team step-by-step guidance when events occur. In short, the execution phase risk model provides a live framework for decision-making under pressure. It transforms uncertainty into structured choices that balance safety, performance, and cost. With risk models covered, let's now move on to time and cost models, which provide the economic counterpart to this risk-based framework. Time and cost models define our expectations for how a well should perform, both in terms of schedule and expenditure. These models operate at different levels of detail. At the highest level, we can forecast whole well performance, but they can also be broken down into sections or even specific BHAs. By modeling this way, we create a framework that can be tracked and compared during operations. Key performance indicators, such as cost per foot, rate of penetration, or rig efficiency, allow us to quantify whether we are meeting expectations. Expected penetration rates are a classic example. If the model predicts 30 meters per hour in a given formation, but we are consistently drilling at 20 meters per hour, the variance becomes immediately visible. The advantage of these models is twofold. First, they give us a baseline expectation, and second, they make performance tracking straightforward. When deviations occur, they can be flagged early for corrective action. Time and cost models set the stage for accountability and continuous performance improvement. Next, we'll look specifically at how these models are used in the design phase to justify and structure the well plan. In the design phase, time and cost models are heavily tied to project economics. One of their primary uses is justification, ensuring that the well design is commercially viable. The models feed into the authorization for expenditure, or AFE, which is the formal approval of project costs. These models also guide equipment selection. If drilling through abrasive formations, for example, the model may justify higher grade bits to balance upfront cost with lower replacement frequency. Contracting is another area influenced by these models. Supplier control and equipment availability are not left to chance. The models give a structured basis for negotiating terms and planning logistics. For example, they may highlight the need to secure casing strings early due to supply chain constraints. Call-out requirements are also embedded. Logistics planning, such as when to mobilize mud systems or additional rigs, becomes predictable rather than reactive. This phase ensures that time and cost are not abstract concepts, but integral to well design. In short, the model provides a commercial backbone that supports both engineering decisions and project approvals. On the next slide, we'll see how these models function in the execution phase, where real-time decisions become critical. During execution, time and cost models transition from planning tools to performance monitors. They allow us to review performance in real time against design expectations. Logistics become especially important here. Call-outs, such as ordering casing or backloading equipment, are guided by the model to minimize downtime and optimize costs. This ensures that critical resources are always available without creating excessive standby charges. Decision-making is another key application. For instance, if a bit begins to dull prematurely, the model helps us calculate whether to continue drilling, pull out, or switch BHAs based on economic impact. Similarly, when faced with a fishing job, the model can guide whether to attempt recovery, sidetrack, or abandon based on time and cost trade-offs. Management of change also comes into play. If actual conditions differ from assumptions, the model formalizes time and cost adjustments, ensuring transparency and accountability. In essence, these models make execution decisions data-driven, balancing efficiency with economics. Having looked at both phases of time and cost modeling, we'll now compare how design forecasts stack up against real-time execution data. Design forecasts and execution realities often diverge, and understanding this gap is key to optimization. Forecasts are built on assumptions about formations, equipment performance, or crew efficiency, but once drilling begins, these assumptions must be calibrated with actual data. One issue with design forecasts is low data density. They typically provide broad estimates that may not reflect daily operational variation. To overcome this, we move to higher density models using daily or shift-based forecasts. These highlight immediate focus areas for the next 12 to 24 hours. Daily forecasts also allow calibration. By comparing actual performance with predicted performance, we refine our models continuously. For example, if actual rate of penetration consistently lags forecast, we adjust future forecasts accordingly. This calibration not only improves accuracy, but also sharpens decision-making. It creates a feedback loop where design informs execution and execution refines design. The key message is that forecasts are not static. They evolve with the data. On the next slide, we'll take a closer look at daily forecasts, specifically how they enhance hazard awareness and mitigation on the rig floor. Daily forecasts are practical tools for bridging design intent with execution reality. They are typically shared during pre-tour meetings, ensuring that the drilling team is aligned on expected events for the upcoming shift. By presenting risks and hazard forecasts, daily updates keep the crew focused on what is most likely to happen and how to respond. For example, if differential sticking is a concern in the next section, the team is briefed on early warning signs and planned mitigation measures. This proactive communication educates the entire drilling team, not just supervisors. Everyone understands both the risks and the responses, creating a culture of preparedness. The daily forecast also fosters two complementary mindsets, proactive and reactive. A proactive team is prepared for likely events and communicates effectively. A reactive team responds professionally and without hesitation when events do occur. Together, these elements create a drilling team that is both informed and agile, ready to handle operational uncertainty. With daily forecasts explained, we'll now summarize the role of forecasting as a whole in driving optimization and continuous improvement. Forecasting plays a central role in the optimization process. By systematically comparing forecasts with actual outcomes, we not only track performance but also continuously improve it. The first key benefit is enhanced performance. When crews know what to expect and how to respond, efficiency improves naturally. Second, decision-making quality improves because choices are based on calibrated models rather than broad assumptions. Another major advantage is early problem identification. Variances between forecast and actual data highlight potential issues quickly, giving us a chance to intervene before they escalate. But to be effective, models must be calibrated. Without calibration, the gap between forecast and execution widens, undermining confidence and performance. Calibration ensures that our models remain relevant, accurate, and actionable. Forecasting and communication together create a feedback loop. Forecasts set expectations, execution provides reality, and calibration keeps the system aligned. With the main content covered, we'll now review our original objectives to confirm how this sub-module has addressed each one. Let's revisit the objectives we set out at the beginning of this sub-module. First, we aim to understand risk models across both design and execution phases. We've seen how they identify, prioritize, and mitigate hazards before drilling, and how they guide real-time decisions during execution. Second, we set out to apply time and cost models to drilling operations. We reviewed how these models justify project economics in the design phase and support real-time performance decisions during execution. Third, we focused on differentiating design forecasts from execution data. We highlighted the importance of calibration to bridge the gap between assumptions and reality. Fourth, we explored daily forecasts as tools for hazard awareness and mitigation, strengthening both proactive and reactive responses from the drilling team. Finally, we emphasized calibration as the key to enhancing both performance and decision-making. By covering these points, we've directly addressed all 5 of our original learning objectives, reinforcing the integrated role of risk, cost, and forecasting in drilling optimization. That concludes Submodule 4 of 4 on Design and Execution. Please proceed to the short quiz to reinforce your understanding of today's material. Thank you for your attention and engagement throughout this session, and I look forward to continuing with you in the next module.